Good morning, students. Welcome to the session on algorithmic efficiency. We know what is algorithm. What do you mean by algorithm? An algorithm is a method or a procedure for accomplishing a specific task. Yes. So later this algorithm can be programmed on the computer. Computer science, it is important to measure the efficiency of algorithms. Why? Because as a programmer, you will have multiple algorithms for the same problem. You should decide which is best for them on a large scale, that is, on a bulk of input data. When I mean large scale, it is really large. It is not thousands or 10,000. It's really huge. Example of large scale, like let's say social networking corresponding to Facebook, where we have millions of users registered. Okay, that is a really large. In that case, Facebook should decide which is efficient algorithm which apt for Facebook. Yes. So as a programmer, efficiency of algorithm plays a very important role. Okay, so the performance of an algorithm depends on many internal and external factors. What are those internal factors? Internal factors it could be the time required to run the algorithm. Okay. Second, it could be the space or the memory required to run the algorithm. And external could be the size of the input to the algorithm and the quality of the compiler, or it could be the speed of the computer on which it runs. Since external factors are controllable to some extent, mainly internal factors are studied and measured in order to determine the algorithm's efficiency, or you can say the complexity of algorithm. So what is this complexity of algorithm? Complexity of an algorithm is determined by studying and measuring internal factors affecting the algorithm. Okay, we are not going to take care of these external factors. We are going to say only the time and space. Now let's see what is this complexity or what is this computational complexity. When I say computational complexity, see, computational complexity is made up of two two words. Yes, what are those words? Computational and complexity. Fine. So what is this computational? Computational means it involves the problems to be solved and the algorithms to solve them. Whereas complexity means it involves the study of factors to determine how much resource is necessary for the algorithm to run efficiently. When I say resource, I think this sentence makes sense. It's quite straightforward. When I mean resource, it means the time to run the algorithm, that is a time which we already saw in the last slide. That is the two internal factors, the time to run the algorithm, the space needed to run the algorithm, that is space complexity. These are the important resources. Now, efficiently, at this point, you should know what is the difference between effectiveness of the algorithm and efficiency of the algorithm. Effectiveness means that the algorithm carries out its intended function correctly. Okay. So efficiency means how does the algorithm? It means the algorithm should be correct with best possible performance. So the measure of efficiency is nothing but to measure the efficiency we need to determine the complexity. So the next slide we will see how we are going to determine the complexity of an algorithm. Very, very important. So to estimate the complexity of an algorithm, that is the time complexity, we are not going to see the space, we are going to see the time complexity of a program for a given input is the number of instructions that this program executes. This number is computed with respect to the size n of the input data. This is how we are going to do. So here I am going to introduce a new term to determine the complexity of algorithm, very important term, that is big O notation. It determines the complexity of algorithm and it compares both algorithms and tells us which is best. Notation is used to depict an algorithm's growth rate. So what is this growth rate? A growth rate determines the algorithm's performance when its input size grows. Okay. Big O is very useful comparing the performance of two or more algorithms and take more decisions. At this point, you should keep in mind that estimation of algorithm efficiency is performed to determine the growth function. That is how the algorithm will perform when the growth of the input size increases. Yes, and it is not telling you the time growth, it's not estimating you the time at which the algorithm is executing. It's a very important point to be noted. Two example. One is having a complexity of big O. This is called O. O is nothing but a function, big O of n square. Okay, one algorithm is working with a complexity of n square. Another algorithm is working with the complexity of 2 to the power of n for the same problem. Okay, for the same problem, we have like a two sorting algorithm and bubble sort and insertion. We take decision likewise in this scenario. So for every input n, how does the n square complexity works? How does it 2 to the power of n complexity works? And then big O will give you which is better. I'm going to put it in the table here. Input 100. If you see n square is having just 10,000 steps, okay, whereas 2 to the power of n steps are very big when compared to n square. This tells you that n square is better algorithm than 2 to the power of n for solving the same problem. Right, clear? Why? How are we comparing using big O notation the performance of algorithm? Now we'll see this page is clear. Okay, let's move on. Now, let's summarize before seeing the examples of various time complexity for the big O. The big O notation includes the growth rate. As I told you, this growth rates tells you how the algorithm grows with respect to the how the input size grows. It doesn't tell you how the doesn't tell you the execution time of the algorithm. Very important. And big O, second, big O, I told you, is a function. Yes, it's a function with the parameter n, where n is usually the size of input to the algorithm. We discussed this in the previous slide. While third, while describing the growth rate of the algorithm, we simply consider the term which is going to affect the most in algorithm performance. This term is dominant term. This term is called dominant. It's a very important term. Example, let's say I have 5n. So there are two possibilities. Big O of n I can consider, or big O of 5 I can take. But big O of, as the input n increases, big O of 5 is really doesn't make sense. It's negligible, right? So which is dominant among them, 5 or n? N. So it takes big O of n. That is the dominant term. Second example, let's take this example, this equation, an square plus bn plus c. Considering a, b, c is a constant, I'm going to eliminate. It plays a very little role, okay? Among n square, n and c of 1, which is more dominant? N square. So always it goes with the dominant term. To dominant term affect the most of the algorithm's performance. Clear? Now we will see the various time complexity and its examples in detail. Okay, time complexity. Let's say big O of 1. Okay, big O of 1 is a constant time complexity. Example, let's say I have an array of element. I want to add an item to the front of the list. It's done by one step. Okay, it's quite straightforward. So this is an example of big O of 1. Next, big O of log n. Okay, here as the n as input size grows, your steps grows logarithmically, not exponentially. We'll see an example. Example is find an entry in the sorted array. Okay, I have a sorted array. Okay, when I have a sorted array, how do I find my, let's say I have a sorted array. Okay, like a binary search dictionary. Then see, where in this case n is the number of items always. And one more important point I forgot to tell you, yeah, big O complexity will always take the worst case of an algorithm only. It doesn't take best or average case. Okay, at worst case it must perform log n steps to find the desired one. Okay, let's say my n is 10, the log of 10 is 1. Let's say my n is 100, my log of 100 is 2. Let's say my n is steps is 1000, log of 1000 is 3. So which means as the steps is increasing massively, my as input is increasing massively, my steps are increasing just logarithmically, not it's not taking exponentially, it's not increasing. Yes, a best example is dictionary. However big is your dictionary, okay, let it be how big, easily you can find the word because all the words are arranged in a sorted order. Another example is your binary search we discussed in our last um, video itself. Yes, I hope you understood the big O of log and complexity. Let's take the next example, that is a linear time complexity, big O of n. Now let's say I want to find the entry in the unsorted array. Okay, so this is the way. N is the number of steps, and you know big O will work on the worst case. It must search the n items to find the desired ones. Let's say interviewer, okay, is going to interview around 20 people, okay, but he has to go to he has to interview all the 20 one by one, but he finds the best person to work for his job only the 20th person. Still he has to go through all the persons. So this is the one case where the array is not sorted, that is n items is equals to n steps. Okay, next uh, yeah next, well, let's see. That's all about the linear. Next, we'll see n log n. Big O of n log n. That is sorting and items by divide and conquer rule. Okay. As the n is number of steps, in worst case, we know it performs n log n steps to find the desired. One best example is, let's say I have a six jeans. Okay, I have to match t-shirts for each of the 6 of my jeans. I go to my showroom. Okay, in the showroom, luckily, I find all the t-shirts are arranged based on the color, size, everything. So this n is nothing but the pant. Okay, number of pants 6. Log n is nothing but the number of dresses in the number of matches for the jeans. So how many matches I will do based, since everything is ordered and divided easily, and easy for me to conquer the best t-shirt. So 6 pants into 3 to 5, that is n log n steps. I hope this is very clear. My next quadratic, okay, which is bubble sort on insertion. We discussed this two sorting algorithm enough in our previous classes. Okay, let's see. For my complexity n squared, n is the number of steps. In my worst case, it takes n into n steps to find the desired one. Let's say I have a recipient, 4 blood groups. I want to match each of this with the donors. Okay, I don't know which. For the best case, it may match to the first only, but my big O works with the worst case. So with this recipient 1, I have to compare all 4. With the recipient A group, I have to compare again all 4. So I have to do this 4 plus 4 plus 4, which is 16. That is 4 into 4, n square, 16. Yes, I hope this is also clear. Let's move on to the next. Okay, next is the last one is 2 to the power of n, exponential. Okay, this is n is where n is the number of items, and at worst case it takes 2 to the power of n. Best example is a game of what is that game? Tower of Anna. Okay, you have 3 towers. I want to shift all this desk to the last tower. Okay, I have to shift one by one, and final location should have the same. So I think it takes 8 steps. Yes, if you see the figure. So for input 3, which is equal to 8 steps. Yeah. Okay. Now that we saw all the examples of big O time complexity, we can conclude big O of 1 takes less steps when compared to the big O of log n, which takes less steps when compared to the big O of n, when it takes less step when compared to the n log n, and thus goes on with n squared less than 2 to the power of n. Yes, I hope you understood this. In the next video, I'll be discussing about the guidelines of computing the complexity by taking various examples like loops, nested loops, if then conditional statements. For watching, thank you.